All right, thanks everyone for sticking around. So as mentioned, this is joint work with Vaishak, Belle, and this is work that was presented in NERPS last year. All right, so this work is on implicit learning, and what that means is simulating learning without an explicit representation. Is popping up, there we go. Okay, so this is in contrast to a more traditional style of learning in which you're given, say, examples, which are, for the purposes of this talk, valuations of the atoms of your language. And a learning algorithm would produce for you rules that are true for those valuations that you got, right? Then typically you would not end with those rules, you would take them and reason with them, right? So maybe somebody wants to answer an entailment query, right? So you want to know if he was entailed by the rules that you learned, by that learned knowledge base, right? So in contrast to that traditional setup, in the setup we consider here, a combined algorithm is given both the valuations of the ground atoms and a query, and basically we want to know if the query was true on those ground atoms, and the type of guarantee that we provide compares to the kinds of rules that we could have learned, right? So we're just implicitly making use of some kind of a learned knowledge base in this combined algorithm. Now, what's the reason for this? So why get rid of the explicit rules? Well, one reason that's been true in the past was that often it was intractable to guarantee that you could learn all the rules that might be necessary in order to decide the entailment of that query. More strongly in this case, though, we'll see that actually it's impossible to learn those kinds of explicit representations, and so an implicit approach is necessary. So in a little more detail, the task that we consider here is we're trying to learn these universal clauses and answer ground clausal queries in first order logic with equality and a countably infinite domain. Okay. So the fragment that we actually want to work with are these proper plus knowledge bases. It's a finite set of universal clauses in which the domain of quantification is constrained by an equality formula, right? So you have equality expressions with Boolean connectives, and then that so you have this quantified clause now. It's just a standard, disjunction of atoms. Okay, and the queries are, of course, ground clauses, right? So that's the reasoning task that we're trying to answer. The learning model is a pack learning model. So the data is drawn from some arbitrary probability distribution on the values of the ground atoms, right? There's no assumption of independence among the values of individual atoms. And it's a partial information model, right? So there's some second process that produces these masking functions, right? Which take the complete infinite valuations of those infinitely many ground atoms and only shows to you a finite subset of them. So in the learning task, you're given some independent draws of these finite subsets of the values of the atoms. And you're also given this ground clausal query, and you want to soundly certify whether or not that ground clause was true with high probability on the complete valuations. So there's a problem here, which is that whenever that clause phi is non-trivial, you can't really learn it, right? That is, we really want to identify clauses that are true with high probability on the complete valuations using only the partial valuations. Now, these universal clauses either are somehow trivial, somehow maybe only a finite number of bindings satisfy that equality formula, or there's an infinite number of bindings that satisfy the equality formula, and they all have to be satisfied in the true full valuation. But in that second case, I can't distinguish true universal clauses from universal clauses which were just true on the bindings that I saw and false somewhere out in the part of the valuation that I didn't get to see. So the solution to this work uses implicit learning. We propose a new testability property that these proper plus knowledge bases might satisfy with respect to this data distribution. We give a reduction of this learning and reasoning problem to the classical reasoning problem. That is, given these partial valuations, we distinguish the ground clauses that were provable from some testable proper plus knowledge base. That's the implicitly learned knowledge base, from those clauses which were not sufficiently true sufficiently often. Thus, it's a sound certification process. And finally, if you have some kind of a polynomial time reasoning algorithm, for example, this Lee-Lacomère-Levesque limited belief system, then we also get a polynomial time learning and reasoning algorithm. And for more, please check out the paper.